Okay. Hello, everybody. In this lecture, I am going to illustrate to you how we can carry out nonlinear regression by using Python and by using LabVIEW. When working with the Python environment, there are two very famous and common fitting functions which are usually used for nonlinear regression. The first one is Scipy-curve-fit algorithm. This is a generic and very common algorithm and could be used with any user-defined nonlinear fitting function. The other function is the Numpy polyfit function, which is specifically excellent working when the fitting function has a polynomial structure. Anyhow, Numpy polyfit function could be used also with any nonlinear fitting function. In order to check the degree or goodness of fitting, we normally use some of the metrics common in this field, such as the R-square score function of a scalar, or we can directly calculate the value of R squared by calculating the mean value of the Y data set and then finding the difference between the mean value of the Y data set and the Y data set itself and the difference between the predicted Y values and the mean value also. This will be clear to you when we calculate this matrix also while discussing this lecture. The value of R squared really should be between 0 and 1. And the nearer the value to 1, this means that the score or the goodness is better. But we have to be keen in advance that R squared matrix is very useful when it is used with linear regression problems, but concerning nonlinear regression, it may not be very trustworthy. Sometimes you find that the value of the R squared is very high, though if you look at the configuration of the plot where the scatter plot and the fitting curve exist, you can see that sometimes, of course, you can see or find that the R squared is very high, but at the same time you watch and find that the coincidence and the agreement between the scatter plot and the fitted curve is very low. Moreover, sometimes the r squared may have a negative sign which cannot be interpreted. So anyhow, just for check, we can use it. We can have an idea about the goodness of fitting by using it. But really, the better way to check the goodness of fitting is by using the mean square error values. To calculate the mean square error values, also we can use sklearn software, which is a Python package also. And really, it is very useful when it is required to compare between the performance of a fitting function and another fitting function. I mean, here the value, which is less, of course, could be considered better. You cannot really say that what is the best value of the MSE, but the smaller this value, the nearer this value to the zero, it means that the goodness of fitting is excellent. Yes. So let us begin our work. After this short introduction, we are going to work with this data set as I am showing you here. We have only one independent feature, which is X data, and the target is Y data. And as you see, it is presented as a list of values, and Y data is also as a list of values. When we plot the scatter plot using X data and Y data, we can see these dots which represent the scatter plot of the data set. Generally, when we want to define the fitting function, we have to consider the configuration and distribution of the scatter plot. The scatter plot here really indicates that an exponent or power function will be very good for this case. So we have selected and defined in advance the fitting function to be as here a multiplied by Numpy exponent of bx. The variables here are a and b, which represent coefficients here, and x here, which represents the variable. So we shall work with this function as a fitting function. In order to find the coefficients as a result of regression activity, we need to use curve-fit, Scipy-curve-fit function. The curve-fit function requires to pass to it the function itself, which is the expression of the fitting function, and the x data and y data also. As a result of that, we can have the two values here, or two objects. One of them represents the parameters optimal values, the values of A and B, and the parameters covariance matrix. Really, the parameters covariance matrix could be used also to find the standard error of each of the parameters A and B. How it is done now, we shall talk about it also very soon. So, as you see, we have an output now represented by the coefficients P of T. Of course, we can extract or slice P of T to two variables. The first of them is A optimum and the other one is B optimum, or A and B without optimum. This is just a name here. And we can print it and have the values. So if we print popped, we shall have two values as a list, or we can also print each of them separately. So as we have done here, if you go down, you will see the optimal parameters P opt are given as a list. The first one is the A coefficient, and the other value is the B coefficient. And that's it. Remember these values: 0.946, this is for A, 0.737, this is for B. Remember it because we shall use the same data set in order to carry out nonlinear regression by using the Numpy polyfit function, and we also shall carry out the same job with the same data set by using LabVIEW. So we need to compare between the results and to find how close they are to each other. So, as you see, practically, curve fitting has ended at this moment, but of course, very often we need to see how the y predicted value, which is this curve in blue, is placed on the plane here relative to the original scatter plot. As we look here, really, they are very close to each other, and this gives an indication that the goodness, yes, of the fitting is high. How we can judge about that? We need to plot at first the curve, and then to find the R squared or the mean squared error. Okay. In order to have an idea about the polynomial function, we can use Numpy polynomial 1D and pass there the values of the parameters optimal values which have been found just now. So here we can find the array of values which represent the polynomial function, and if we pass as a parameter the x data, we can find the y hat or the y predicted values. This y hat could be plotted and represented as it is shown here in blue. So here you will see that where it is plotted here. Yes, this is the predicted value here. And here it is. So we have plotted it directly by using the first parameter as the X fit, which is, as you see here, an array of values created by us called X fit with a range from 0 to 10 and a step equal 0, 1. If you divide 10 by 1, you will have, by 0.1, you will have 100 points. So this is the array which represents the X values. Here it is X fit. And now the function, here it is our function, the fitting function of X fit. And now we pass the optimal value of A and optimal value of B. In this case, we can plot directly the blue line, which represents the prediction curve or predicted curve. Okay, now what we are going to do, we are going to check the fitness or the goodness of our work. The first method to do that is by calculation through a simple program, as you see here. We use Numpy mean function and pass there the y data. This is given to us here. This is the y data. This is the target values. And we find the mean value y mean. And now we use the difference between y data and y mean, and it is squared, and pass it as an argument to Numpy sum to get an object, we call it S total. The same thing we do with the y hat, the predicted values. Here it is values, predicted values. Y hat or predicted value, the same thing. I have written for you here that you find the difference and square it again, and you find SS regression. And now you find the ratio between SS regression and SS total. You will find the R squared. If we print it here, we will find this value 0.403. As you see here, this value really lies between 0 and 1, though it is not very close to 1. And as I told you, this gives just an indication, but not an exact answer to the goodness of the fitting. Let us try to find it again by using a scalar. By using a scalar, we import in advance R square score from the metrics of a scalar library. This is a library, a scalar Python library. We call the metrics, and from there we import R square score. R square score now is used here, and we pass to it the two values, the y data and the y predicted or y hat. And directly we get the R squared. If we print it again here, we shall see that we have got again exactly the same value, 0.403. So concerning the finding of this value, there is no suspicion about that. It is exactly the same value achieved by two different ways. But as I told you, it doesn't give an exact answer to the goodness of the fitness. Preferably to work with the mean square error matrix. And as smaller as this value, the smallest this value, the better will be the fitting of the function with the data set. How we do that? We can use we also can use sklearn. So from sklearn, we import matrix as we did before, and from there we import mean squared error. We do not import R squared, we import as here, as it is here upwards, import R squared score. No, we did not import it, not necessarily. We import the mean squared error. Now we can use this imported object, mean squared error, and again pass to this function the y data and the y hat data, and we get directly the MSE, which is the mean squared error. The mean squared error here in this case is found relatively high, 288,850. It is relatively a high value and not close to zero, though we see that here in the figure they are very close. One of the reasons for that is because the scale of the ordinates here and the values is very large. Anyhow, we shall consider this value and compare it with the results which we will achieve when working with the polyfit, Numpy polyfit function, and when also we shall find the MSE when working with LabVIEW. But remember also that this number is anyhow high and not fascinating. Okay, so what we have done just now, I have introduced you to the curve fit, which is Scipy-curve-fit function, and how it could be used to define the coefficients. We are not interested here with the covariance matrix of the coefficients, so we did not work with it, though we can, of course, work with it and take the square root of the diagonal values to define the standard error for each of the coefficients. Maybe we shall do it in another example. Okay, so now let us go and try to do the same, but with another function, which is the polynomial fit function or Numpy polynomial function. So, for the sake of comparison, we shall take the same fitting function and we shall use the same data set. So how fitting is carried out? It is very easy here. At first, of course, we have plotted the plot of the initial values where the feature represents the x and the target is represented by y. The maximum value here, 1,500. Here it is about that. 1,500 is this ordinate for this value. So these points represent our data set, as we did before. But now we apply Numpy polyfit instead of applying curve-fit function of Scipy. The Numpy polyfit requires only the dataset values x and y, and what is the order of the polynomial fit function? What is the order to be used? Here I have given the order 2. When you give order 2, here you will have 3 coefficients. If you have order number 3, you will have 4 coefficients. If you have number 5, you will have 6 coefficients. So applying polyfit to these data sets gives you the output, the coefficients values. The coefficients here are A and B and C, 3 values, because the order, as I said, is 2. If you print A and B and C, you will find them here. This is the value of A. This is the value of B. It is negative. This is the value of C coefficient. These are the 3 coefficients which result and define the polynomial function. Of course, if we pass these coefficients to the function Numpy polynomial 1D, as we did with the previous example, we find the polynomial model itself. And if you pass to the polynomial model the x values which is necessary to use, you can get the y hat or the y predicted values. So to do that, after having the polynomial model itself, we create a new dataset to be used by the polynomial model. We pass it, we called it a new x new. It is also existing between the minimum value of x and the maximum value of x. And the number of values is given as 10. And the predicted values are given through this object. So in order to plot it, you just take y predict and plot it. PLT plot, x value and y predict, you give it color red, it will be shown as a red color. As you see, this fitting curve is really very close to a parabolic function or a squared function, because we have taken the second order of the polyfit function here, 2. Now, when we took the r squared or found the r squared, as we did before here, by using r squared score from sklearn, and we have printed it, now it is about 0.899. It is closer to 1 than we have got before by using Scipy-curve-fitting function. In this case, it is really closer to 1. This is noticeable. And also here we have imported the mean squared error function from sklearn again to find the value of the mean square error, and we have found that the mean square error here is 20,722. This is much less than the value which we have got before, which was 288,000. Here it is 20,722. So as you see here, the r squared and the MSE give indication that fitting here with the polyfit gives a better result. And now the question arises, are we satisfied with this? I can say no. Why? Because the mean square error could be reduced if we raise up the order of the polyfit function here from 2 to 3, or from 3 to 4, or to 5. I have done this again here, and I have given the order 5. So we shall have 6 coefficients now. 1, 2, 3, 4, 5, 6 from A to F. Now, if I print the coefficients here as a result of fitting the X data and the Y data, I have coefficients. If I print the coefficients, I shall have 6 values. 1, 2, 3, 4, 5, 6 values. Now, again, I have passed the coefficients to the NPy poly 1D to create an array which represents the polynomial mode, and then extracted the predicted values. The curve will be as you see here. And when I calculated the mean square error in this case, now mean square error, here it is now 142 only. So it is drastically reduced from 288,000 to 20,000 to 142. So again, if I take the order a little bit higher here, maybe I shall have also a less value of the mean square error, which means the fitting is becoming very accurate and very acceptable. I hope that this is very clear to you now. We have examined the Scipy-curve-fit function, and we have also examined the Numpy polyfit function twice with 2 different degrees, and as you see, we have found that the results are acceptable. Okay, now we shall do the same curve fitting by using LabVIEW. So we quit from the Python and go to LabVIEW to demonstrate to you how we can do the same there. We shall work with this virtual instrument, and at the same time, we shall work with the same data set. This is intentionally so that we can compare between the results. So the features which we have is only one feature X from 1 to 10 as we have before, and this is the target from 1 to 1,500. So these points here represent the plot of the data set, the original data set. The curve in red here represents the fitted line. How this is done? If we go to the front, to the block diagram, we see this is the terminal of X. The values of X now are here. This is the terminal of Y. Both of them are fed to a function called exponential fit.VI. If I right-click here and go to mathematics, to fittings, here you will find this function, exponential fit.VI. So we are working with this function because the curve also is exponential. Of course, I can take it and put it here and work with it, but it is already existing here, so there is no need for it, just to show you how we do it. So the inputs X and Y are supplied to the exponential fit.VI. It requires to define the method to use. Here is the least square method. This is the acceptable tolerance. I have put it to, as you see, 0.001. Not very strict, but it's okay. And now, what do I have as the output? As the output, I have the amplitude, which is the coefficient A, and the power, which is the coefficient B. So if I go to the front, to the front panel here, remember the amplitude .946, the same value which we have got when we worked with the Scipy-curve-fit, and the power, or the other value, which is .737. Exact values, the same values we have got here. At all, no difference. Now we go back to the block diagram, and we want to plot these dots, and we want to plot the fitting curve. So to plot the dots, we take X and Y together. As you see, X is taken as an input to this, sorry, to this bundle. And what I have done, I want to write its name, bundle, and this is another bundle. So here is X array, and here is the Y array, and both arrays are fed here. Really, if I take this output, this cluster, to an XY graph, I can have only the plots. If you want to see, if I, sorry, okay, if I take the graph here, XY graph, and put it here, and go back to the block diagram, here it is. If I connect this output to this XY, here I shall have the dotted values. If I run the program, as you see here they are. If I want to show them as dots, I go and show them as, here they are the same. But I didn't want to show them. I wanted to show them with the fitted curve overlaid there. So anyhow, you know now what does it mean. And I have taken out from this exponential fit the best fit values. This is an array of values. Here it is taken by me here. It is best power fit. If I double click it, you shall see these values. And these values really which describe the ordinates of the red curve. So what I have done, I have also used another bundle where the first value is the X. This is the X array. This is the X array. And this is the best fit, or the Y predicted values. And again, if I draw this alone, I will get only the red curve here. I have taken this curve and this curve together and added them together by using an array, build array function. And now here I have them both together. So we have drawn the existing data set as points to differentiate them from the predicted value, which is in red here. Again, if you go and look at the output here, you find that I have taken also the Y, the input, which is Y, from where I here, sorry, where is y? Here, this is the predicted value. This is y, should be y. It is taken from here. I think this is the value. The best fit. This is the best fit. And what is this here? This is the best fit. I should put here y. Let me take this away and connect it as you see here. And now if I run the program, this is the goodness. It is very close, the same. 0.99, which is about 1. So the goodness, this is the goodness function. Let me write it to you. Goodness fit.VI, which gives us the output, of course. Why do I'm doing? Windows, show block diagram. Here they are. So this is the goodness fit VI. How to find it? You can go to the mathematics, again, to the fittings, to the advanced curve fitting, and there you find it here, goodness of fitting. Goodness of fitting. How to work with it? You can go to the help also, and you will find there nothing to do. You have just to supply the y and y predicted value so that it compares between both and gives you the output, the r square value. Now we found that it's about 1, and the root mean square error, it gives the root mean square error value. Here, the root mean square error value is 75. If I run it, to be sure, it is 75. This is the root. So the mean square error value now, it will be 75 squared. It must be squared to give you the value. Remember, when working with the curve fit, it was 288,000. Here, if you want to see it, here, and you can square it, numeric, this is where x squared, without taking the root, and take here an output, an indicator. Now this value here will represent the root mean square, not the root, the mean square error, which is about y. It should be higher than that. I have taken it from here. I don't know why. It should be taken, the root mean square should be squared here to get the value. So it is about 5,626. Remember, when we have worked with the curve fit, it was 288,000. And when we worked with the polynomial function, it was with the degree number 2, it was about 20,000. And when we worked with the polynomial fit with degree 5, it was about 140. Here it is about 5,625, which means that this is equivalent to a polynomial fit function with a degree about 3. It seems to be about 3. Okay, so as you see, we have got, yes, here it is. No, this is the residual. So as you see here, we have also done the same job with the same data set and found the best fitting array we have drawn this best fitting array over the plot, which is shown in dots, and we have found the mean square error and analyzed how the system works. Okay. What we can also show you. Let me go to see example 65.1. Yes, this is another example related to the subject. As you see the title, I have written generate power data function and realize power regression. So I have at first to generate a data. And then I have to carry out the regression to this data. In order to generate the data, really, I wanted to acknowledge you with this setup here. Here I am using a ramp pattern VI. It is in LabVIEW also. You can go to the signal processing, signal generation. Here it is, the ramp pattern. If you want to know more about it, you can double click it and go to the help. But it generates an array of values beginning from a start point and ending with the ending point. So this function has a start value. This is the start value. It is given 1 as I wanted, and it has an ending value, which is, I think, 10. Here, the ending value is given 15. Yes? Now, I have generated the array with a number of values defined by the number of points here. The number of points is 15. So the step is number 1. Taken 1. So now the array is generated here at the output. This is an array of values beginning from 1 and ending with 15. This is the array. If you want to see it, double click here. You will see it here. Now, I have taken a function called power of x. It has two inputs, as you see. Here x and here power of x. For example, x to the power b. How and where it lies? Very easy. You right-click, go to mathematics, go to the elementary functions, exponential functions, and here it is, exponential function. Or you go to this function, power of x, which I am using, x to the order of y. If you take it here, you will find two inputs. This is x and this is y. The output here will be x to the order of y. So this is which I am using here. X to the order of y, of b, sorry. This is b now, a given value. It is taken by 9, I give it 9. And a is taken also as a constant value here. This is a. Now a, this is a, multiplied by the exponent of x, which is here. This is x to the order of b. This is the same function which we used as a fitting function by using Python. So this is the output here. I have added a noise to the output. And now this is the output array complete. This is the exponential function with some noise. This is the function with added noise. Now, if I want to carry out fitting of these functions by using the power fit VI, Practically, I know the coefficient A and B in advance. So what do I expect if I run the program as a whole here? And I use this fitting function here, power fit.VI, I have to get exactly the same values here, B and A. So at the output here, the fit amplitude and fit power must be 7 and 9. Here it is dot 7, and the other one, the power will be 9, which is here, dot 7 and 9. At the output, they should be dot 7 and 9. So this is the original set which I have generated. This is the function itself for fitting, and here they are overlaid on each other. And if you want to evaluate the error, it should be about 0. It should be about 0. Let me go. Here it is, the root mean square error. First of all, the r square is 0 taken, and the root mean square will be 0 because exactly the same function. So if I go to the block diagram here, as you see, and I have used the goodness function. At the output, I have found the r square and the RMS value. I found them exactly equal to 0 because the generated array, which is here, exactly is the array which I have used as input. I hope this is a good test for the algorithms, and also it demonstrates to you how you can generate a data set with a given configuration as a power or as an exponent by using LabVIEW. Because when we used it with Python, I didn't explain to you how it is done because it is just a formula. Here, it is the same formula, but you have to build this formula by using the block diagram elements. Okay. What else I can show you here? 65.2. Maybe there is something interesting also. It is very interesting. Please be patient, please. Here I am using a very interesting virtual instrument in LabVIEW. This is one of the sophisticated virtual instruments called Express VIs in LabVIEW. One of these Express VIs is curve-fitting VI. How you find it? Very easy. You right-click on the block diagram, and then you go to the Express here. You see Express. You go to the signal analysis, and you will find there curve fitting. You take this and put it here. It is opened now and makes facilities for you to select what type model you want to use. Are you going to work with linear curve fitting? Or this is red line. This is the original data set which we have. Or you want to work with a quadratic polynomial with an order number 2, spline, or polynomial. Here, polynomial order is given number 5. Of course, you can decrease it to number 4, to number 3, to number 2, as you want. Also, you have the facility to work with regression where nonlinear regression takes place, or you can use general least squares linear method, which is very similar to the OLS. So this is a marvelous thing here. Let me work with you here, okay, with it and explain it to you in detail. So when I put it here, as you see, there are terminals from this side, which is the inputs. There are terminals from this side, which are the outputs. The signals represents the target, the Y value. Here it is. If you go here, it is the Y, which is the dependent variable. Signals. The locations represents the feature or the X, which is independent variable. So this is the dependent variable, this is the independent variable, this is the data set which we are going to work with. I have taken it exactly the same as we did before. Look, this value is the Y from 1 to 1500, as we did before with Python and as we did before with LabVIEW. And this is the X values. So they are existing at the input. What it gives you as the output? It gives you the best fit. This is an array, must be an array here, with the values which represent the Y predicted values. But here it is given as an output, displayed output. If I take it away here, let me take it away and right click here and go to create. It asks you want to create a numeric indicator or a graph indicator. I wanted it to be a graph indicator. So I have just, instead of this one, it is already connected graph indicator. This one now has to be cancelled. Additional one now it became. If you want to have a numeric indicator values, as I expect, it should be an array. So let me take it away and take this away. And now I again right click it here and go to create a numeric value. Here it is given as the last value and not as an array. So what I have done, I have taken this is a value, this is not an array. So I have taken this away, I don't need it. And now I again select to create an indicator. And now this indicator, maybe now if I make array indexing like this, now I have this array. If I put here an indicator, now this array will show the values in parallel with the graph. If I double click it here, it is here. Now leave it in place, it is a good place. If I run the program again, now these are the values which represent the best. These are the values which are the points here of this curve. Now, so I have gotten this curve. This curve here is this one, which is the output, and this curve practically is the same. This is best fit 1, best fit 2. How they are? This will be shown to you just one moment. If I if I right click on this VI anywhere here, right click and go to replace, and I have the option to replace with any fitting palette, from here, I have selected the exponential one. Where it is the exponential one? Here, linear, here it is. This is the exponential VI. So instead of having this configuration now, I have this configuration, new configuration, which is this one here. I have substituted the original curve fitting by an exponential VI. And then I connected the inputs and outputs as I want. Again, maybe you did not understand me. So if I go to the Express, signal analysis, then to curve fitting, I will get this VI. Okay. Now I have this configuration. I would not want to work with the values. If I double click here on this icon here, I shall have these options. I do not want to work with these options. I wanted to work with a VI, which is from LabVIEW palettes. So I go there, not here. I go here, right click it, go to the replace and to the fitting palettes and select the palette which I am want not to work. I have selected the exponential fit. Here it is. Now having this, why I did this, I selected it specially to compare between the performance of this exponential and with this curve fitting. So again, I have connected here the input and the output. And here is the output now. Best exponential fit. It is now an array. This array, if I look at it, it should be very close to the array which I have found here, this array. If I go to this best fit, this is, I have to create here an indicator, create indicator. This is the indicator. And now if I double click it, it is this one. If I drag it beside or here, beside this one, and I drag it now, I should have very close values. They're very close, but they should not be exactly the same. Now, I have the curve of best fit. At the output, I have the amplitude, which is the value, and the damping here is the order. And if I compare them or I try to find them, remember this value, the amplitude 0.946, and the power, which is 0.737, exactly the same values which we have got with the Python and which we have got with the LabVIEW in the previous case. So, as you see here, really, also, of course, I have used the input, the predicted values, and try to find the goodness of the function and to find the RMS value and R squared here. And the RMS here also is 26. And when it is squared, it gives you 562, which is very low and very acceptable. And the R squared is about 1, as we did before. If you square the 26, and here is the other value, which I have got it myself here. I have extracted it. Here it is. At the output here, the mean square value, I have taken the square root of it. I have found the square root mean value, which is 23 instead of 26, which is practically the same. So, as you see, there are a variety of activities and possibilities, really, which you can use to manage curve fitting, nonlinear curve fitting by using LabVIEW. And I advise you to try to practice yourself with curve fitting Express VI and how you can replace it with any other function in the palette of regression or in the palette of LabVIEW curve fitting. And I think with this, we came to the end of our lecture. And I hope that this is very useful to you and that you understand what I have said. Thank you very much and a happy day for you. Okay, with this we finish. We go out. Don't save, I want to save it as it was. Stop share.